In this segment, we'll talk about how do we solve an integral as a solution to a first order ordinary differential equation. It'll go all back to the fundamental theorem of calculus to be able to see that, hey, if we can solve an integral by using a solution to a first order ordinary differential equation, what that means that if we have numerical ways of solving an ordinary differential equation which is a first order, how can we use that to also be able to hence numerically integrate a function? So in order to understand this, we have to look at the fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus. One is that if the function f of x is a real valued and a continuous function in some interval d, then what you can say that, hey, if a is a point in this interval d and you are integrating this function f of x from a to x, so in this case you are integrating f of t, which is a t being the silent variable here, which used to be called a dummy variable many years ago. So you have g of x is equal to go from a to x f of t dt. So you're integrating the function f of t from a to x. Then since this is a function of x, if we take the derivative of that, what you're going to get is this function back. Might seem to be very simple now, but when you took your integral calculus class, this came very handy because you're already taken your differential calculus class and you were able to use all the derivatives which you have found to be able to reverse engineer to find out what the integrals are. So let's suppose, let's take an example. Let's suppose you have the function f5 t squared. Then if I integrate this function from a to x, I'll use my integral calculus knowledge, I'll get this, right? And from there, I'll get 5x cubed divided by 3 minus 5a cubed by 3. And if I was going to, so this is my g of x here now. If I take the derivative of that g prime of x, I get 5 divided by 3 times 3x squared plus minus 0 here because this is a constant, and I get back my 5x squared. So that's all there is to it. That if you have a function which you're integrating and from a to x, then you'll get a function of x, let's call it g of x. Then if you take the derivative of that, you're going to get the integrand back. There's a second part to this fundamental theorem of calculus. Some people call it the second theorem, but there's only one fundamental theorem of calculus. This part 1 and part 2 to way to look at it. Now here we have a function which is real valued. We don't have to even assume now it's continuous. That is sometimes the beauty of this particular part of the fundamental theorem of calculus, that if it's real valued in the interval a comma b, then if g of x is the antiderivative, so that means that g of x, g prime of x is simply f of x. That's what it means, that g of x is the antiderivative of f of x. Then you will get this, because the g prime of x is f of x. What is going to happen is that, hey, when you integrate f of x, it'll be just the value of the function at b of this g function minus the value of the function at a. So here I'm showing you both part 1 and part 2, but I'm showing you part 2 first and then I'm showing you part 1, because when you look at the combination of the part 1 and part 2, what you are basically seeing is that, hey, that if I want to find the value of the integral f of t, I can always write it as dg by dx is equal to f of x. This can be written as this. If you look at this, this is like an ordinary differential equation. Now, if I say that the value of g sub a is 0, now go here. If the value of g sub a is 0, then whatever turns out to be the value of g sub b will be the value of this integral. Because if g sub a is 0, then you know that the value of the integral is simply the value of g sub b. So this is how you are converting a problem which is imposed for integration into a problem of an ordinary differential equation of first order form, which is of this form, to be able to solve. So what that means is that, hey, somebody can give me a differential equation which is like this, with the initial condition that g sub a is 0, g sub a is 0, I'll say find g sub b, and that would be the value of this particular integral. I'm using the knowledge of solution of ordinary differential equations to be able to find the value of an integral. Now let's go and look at this through an example. Let's suppose somebody is giving you an integral going from 3 to 9 5x squared dx, and keep in mind that we are in the chapter for ordinary differential equations, but as I mentioned to you, I showed you that how the two procedures are related to each other, the integration as well as solution of ordinary differential equations. So we have two parts. One is to calculate the value of the integral using our calculus knowledge. The second one is to pose the same problem as an ordinary differential equation, and then using our knowledge of exact solutions to be able to find the value of the integral and see if they are exactly the same. Now keep in mind that we're not using numerical methods here. We are purely using a knowledge from your integral calculus as well as your ordinary differential equations course. So let's do part A first, which is the simpler one. So if I want to integrate 5x squared dx from 3 to 9, this will be 5x cubed divided by 3. Going from 3 to 9, this will be 5 times 9 cubed divided by 3 minus 5, 3 cubed divided by 3, and this is 1170. So that's part A. Let's look at part B. So here we're going to talk about part B, and I wanted to revisit this particular part right here of the Fundamental Theorem of Calculus, that if g of x is the entire derivative of f of x, then this is true. So what that means is that our function f of x is 5x squared. I'm going to repose the problem as df by dx being 5x squared. That's what I'm going to do. So, or I should have said dy by dx. Dy by dx is 5x squared. And then what I'm going to do is I'm going to say that the initial condition of y at 3 is 0, because that is the lower limit of the integration. And I'll say, hey, find y sub 9. Then y sub 9 itself will be the value of the integral 3 to 9 5x squared dx. So this is very important to understand it, that you are taking this problem here and you are now posing it as a first order ordinary differential equation. You are assigning an initial condition that at the lower limit of 3 the value of y is 0, and let's go and find y sub 9, and then y sub 9 itself becomes the value of the integral. Keep in mind that there is no imposition on you to choose y sub 3 equal to 0. You could choose y sub 3 equal to any number you want, but it is still the difference between y sub 9 minus y sub 3. What choosing y sub 3 equal to 0 gives us is that, hey, y sub 9 is directly the value of the integral. Now what we're going to do is we're going to solve this ordinary first order ordinary differential equation by the techniques we have learned in our ODE class, and it's going to be a little lengthy, but it is not complicated. Let's look at this this differential equation which we have, first order differential equation. We have dy by dx equal to 5x squared, we have y sub 3 equal to 0, and what we need to do is find y sub 9. Let's go to our classical solution technique, which says that the total solution is equal to the sum of the homogeneous part and the particular part. What the homogeneous part simply corresponds to is that, hey, that this part is equal to 0. There is no forcing function as such. So we know that the characteristic equation corresponding to the homogeneous part of this differential equation will be the coefficient of dy by dx, which is simply 1, and will be m to the power 1, which is the first derivative here, and that's it. It will be equal to 0, and that gives me m is equal to 0. Since m is equal to 0, then the homogeneous part will be k e to the power mx, which will be k e to the power 0x, and that will give me just k. Now if you look at the particular part of the solution, will be the form of the right hand side, or the form of the forcing function, and all its possible derivatives. So that would let me write down that, hey, this is the form of the particular part of the solution. But as you can see that this part right here is part of here. So you have a particular solution part which is same as the homogeneous part. So we cannot accept that. So we have to choose the next independent solution. So we'll get something like this. So that we get ax cubed plus bx squared plus cx as an acceptable particular part of the solution. There's no conflict then with the homogeneous part. So what we'll do is we'll define a, b, and c. And how do we do that? We plug it back into the differential equation. So we have dy by dx. So we'll have dyp by dx will equal to 5x squared. And let's see what this gives us. So we have the homogeneous part of the solution is now, sorry, particular part of the solution is ax cubed plus bx squared plus cx. And we have to put it equal to 5x squared. So this gives us 3ax squared plus 2bx plus c equal to 5x squared when we take the derivative of it. And what I'll do is I'll write this as 0x plus 0. And the reason why I'm doing that is because in order to find a, b, and c, I'll have to equate the coefficients of the second order polynomial, which I got from the left side, to the coefficients of the second order polynomial on the right side. And since there are no more terms, I will just add 0x plus 0. So this gives me 3a is equal to 5, gives me 2b is equal to 0, and gives me c equal to 0. So from here, what I'm going to get is a is 5 by 3, b is 0, and c is 0. Hence, the particular part of the solution is nothing but 5 by 3 x cubed, because b and c are equal to 0. Now let's go and see that, hey, how we can combine the particular part of the solution and the homogeneous part of the solution and be able to write down what the complete solution is. So the complete solution will be y is equal to yh plus yp. We found out the homogeneous part is a constant. The particular part is 5/3 x cubed, and that's what we have. So what we have to do is, this is k, and we have to find what k is. But we also know that y is given at 3 is given as 0. We have the initial condition not at 0, but at 3, which is the lower limit of integration. Y sub 3 is 0, so that means 0 is equal to k plus 5 by 3 times 3 cube right here. And that gives me k is equal to minus 45. And once we have k is equal to minus 45, we have the complete solution. Y is equal to minus 45 plus 5 by 3 x cubed. And if I want to find what y sub 9 is, y sub 9 will be this, and that gives us 1170. So in fact, the value of y sub 9 is the exact value of the integral going from 3 to 9, 5x squared dx. And we got that by using our integral calculus knowledge. We got that by using our ODE knowledge. So again, what we got to understand is that, hey, this did not turn out to be a magical thing. Why? Because we have this, that, hey, if we have an integral, and that will be equal to g sub b minus g sub a, provided that g is the antiderivative of the function f of x. And we are able to reimpose this problem as dg by dx equal to f of x with g at a equal to 0. Then g of b is the value of the integral going from a to b f of x dx by using the two parts of the fundamental theorem of calculus. And that is how we have to see that, hey, when we go to numerical solution of ordinary differential equations, that we will in fact be able to use the numerical solution of ordinary differential equations to be able to also do numerical integration as well. And that is the end of this segment.